All right, 3.1 is basic rules of differentiation. We ended chapter 6 on section 2.6, where we were talking about using the process of finding the limit of the difference quotient to find the derivative. Today, we're going to learn how to go about that in a shorter way, which is to use basic rules of differentiation, not really formulas, but just sort of ways that you're going to work with different types of functions. We're going to be spending some time on that today, and then we're going to learn a couple of different methods for working with different types of functions as we move through this chapter. So this whole chapter is basically just going to be about how we're going to find derivatives using derivative rules. But you'll probably like this way more than you enjoyed finding derivatives using limits. So we're going to apply the basic differentiation rules to find derivatives, slopes of tangent lines, and equations of tangents, and continue to apply derivatives to applications. All right, we're going to have to talk about some notation first. We talked last time about f prime of x, and we're going to keep using that notation as well. But consider the example of f of x equals x squared or y equals x squared. The following all denote the first derivative. So these are all different ways of saying the same thing. So f prime of x is 2x. That would be the derivative. Or y prime is 2x. Those are saying the same thing. We could say df dx is 2x. This is just saying the derivative of the function f with respect to the variable x. Or more commonly, we would say dy dx equals 2x. So these are all just different ways of saying the exact same thing. So don't be thrown off with this whole, like, what is this dy dx business? It's just y prime or f prime of x. You're not going to see df dx quite as often. Usually when I use this notation, I'll use dy dx, but either one of them is fine. By the way, I have to tell you, I had this paper sitting out last night because I was going to record this video today, and my 5-year-old came over and he was like, "Hey, that's Miss Meredith from school." Okay. Anyway, Newton and Leibniz are the originators of calculus, and each one of them had different types of notation that they would use, which is why we have different notation that we use to talk about derivatives. Anyway, so let's continue to talk about this. We can write the statement d dx of x squared equals 2x, which says that the derivative with respect to x of x squared is 2x. So if you're trying to translate these mathematical symbols into the English language, this is the way that you would say that. So d dx of x squared is the derivative with respect to x of x squared is 2x. We always have that equal sign being is. All right. So we have that. Now, basic rules for differentiation. This is outrageously important. These are the rules that you're going to be using for the rest of the class. These are extremely important to you. Rule number 1, the derivative of a constant. So here you're taking d dx of some constant number. It could be any constant value, but you're thinking something like 3, -5, 1600, the square root of 17, any sort of constant number where you don't have a variable involved. The derivative of a constant is 0. The reason for that is because the slope of a constant is 0. If you consider, for instance, maybe, I don't know, the function f of x equals 2, well, this we would also think of as y equals 2. This is a constant function. And if you remember from algebra, the way that you would graph that is it's a horizontal line through 2 on the y-axis. So this is what the graph of y equals 2 would look like. And 2 is a constant function. Remember that the derivative is a slope. So if I was trying to find the slopes of the tangent lines at y equals 2, all of those slopes would be 0. 0 slopes, remember, don't have any rise. They only have the run. So the rise would be 0 over some number that you're running. Therefore, that's where this comes from. The slope of a constant is 0. The derivative of a constant is 0. Don't get that confused with the limit of the constant. So the limit of the constant was that constant itself, because we would just be doing direct substitution for the limit. But with the derivative of a constant is 0. Just remember it, but if you are like, I can't remember it, you can always go back and graph this constant function. So that's important. The power rule, really, really important. So for the power rule, we're taking the derivative with respect to x of some function where you have x to the nth power. Now, in this case, we're going to take the nth power and put it in front of the function. Then we're going to rewrite the base of the function, which in this case is x, and we're going to decrease the power by 1. So this is your power rule. What that would look like would maybe be if you had f of x equals x cubed. Well, you would find f prime of x, which, by the way, is the same thing as saying dy dx. Get used to working through with this notation. The derivative would be, well, you're going to move the constant in front of the x, rewrite your x, and decrease your exponent by 1. So your derivative would be 3x squared. That's how the power rule works. You could also see that, though, for more complicated exponents. Like, let's say that we had f of x equals x to the -5/2. I know sometimes when we see a negative exponent, we want to make it positive, but in this case, we actually don't want to make the exponent positive by moving the x into the denominator. The power rule only works if the x is in the numerator, or just by itself, I want to say, the only variable, and it's not in the denominator. We're going to go through some examples of how you would simplify to match this rule in a little bit. But to take this derivative, f prime of x, we would take the exponent and move it down in front, rewrite the x, and then when we decrease the exponent by 1 in this case, it's becoming more negative. So if I take -5/2 and I subtract 1, I'm taking -5/2 minus 2/2, which actually gets me to -7/2. Now, if you wanted to write this, side note, with a positive exponent, you could move the x into the denominator. So I'm going to leave the 2 right where it is in the denominator. You would move the x into the denominator, and then you would make the exponent positive. Oh, I forgot to write the 2, sorry. So we're going to be working with rewriting all of these expressions, but I wanted to remind you of how to do that. All right, so that's the power rule. The last rule we have on this page is the constant multiple rule. This is just saying that if we're taking the derivative of a function that's being multiplied by a constant number, we can just take its derivative and multiply that by the same constant. So this would just be whatever k is times f prime. So no big deal there. And this would be, for example, let's say we had f of x equals 5x cubed. The constant multiple in this case would be 5. So you're just going to apply the power rule to take the derivative just like you normally would, just like we did for illustrating the second rule. Notice we had x cubed there also. And you're just going to multiply 5 by that derivative. So the 5 stays where it is, and then you bring the 3 down, rewrite the x, and decrease the exponent by 1. So you end up getting, now you have 5 times 3, which is 15, x to the second power. So those are your derivative rules. Okay. The last one, it's sort of a combination of the other rules, is the sum and difference rule. This just says that if you're taking the derivative of the sum or difference of 2 functions, you can rewrite this as the sum or difference of the derivatives individually. So it's like taking f prime of x plus or minus g prime of x. So if you're just dealing with taking the derivatives of a bunch of terms, you can just take the derivatives of the terms separately. And the sum rule is illustrated by this proof here. You can check that out. I'm going to add another rule here. Just It's not really another rule, but sometimes I feel like it's helpful to kind of split it off. The derivative with respect to x of just x, officially this follows that power rule, and I'll show you why. But the derivative of x with respect to x is just 1. And that's because by the power rule, when you take the derivative of x, you're doing f prime of x equals, and then you would move the exponent down. So the exponent on x is 1. You would rewrite the function, and then you would subtract 1 from the exponent. I subtracted 0, though, which makes no sense. It's because I was so bad in my mind. Okay. And then you would subtract 1 from the exponent. So this would just be 1 times x to the 0. And remember that x to the 0 power is 1. So if we're just finding the derivative with respect to x of x, it's 1. Of course, we could also use that with a constant multiple. So if we were looking for the derivative of 2x, the derivative would just be 2. So on and so forth. Sorry, I'm like super stuffy all of a sudden. It seriously just started once I was talking. All right, so I'm going to go through some examples here of how to find the derivative. We're going to combine a bunch of these rules. I'm going to put 2 examples on this bottom portion of your page. The second one is going to be a little bit longer. The first one will be quick. So example 1 is f of x equals 3x to the 8th minus 6x plus 9. To take this derivative, the first term is going to use that constant multiple rule with the power rule, since we're using the power rule for x to the 8th, and it's got a constant multiple of 3 in front of it. And then for this 6x, I'm really just going to be using the power rule, or just think about it as using this x rule. And then for 9 is just a constant function. So we're going to use all 3, or technically we're using like 3 rules. So to take f prime of x, I'm going to use the constant multiple rule first. I'm going to bring the exponent out front. I'm going to rewrite the x, and I'm going to decrease the exponent by 1. So I'm going to take 8, subtract off 1, that gets me to 7. Now, the constant multiple here for negative 6x or minus 6x, I'm going to write the 6 down, and then the derivative of x is just 1. You're not going to probably write that as you're going through this, especially on your test or on your homework. You're just going to start taking derivatives because these are going to become very quick for you. But for right now, I'm just sort of illustrating the rules. So I'm showing all the steps. And for a lot of you, this is the first time you've ever seen derivatives. So I want to make sure that all the steps are there so you're clear on what's happening. As far as the 9 is concerned, the derivative of any constant is 0. That was the first rule that we went over. So this was the constant rule. What did we call it? What did we officially call it? It was called Rule 1, the derivative of a constant. So yeah, this was Rule 1. Technically, the power rule was Rule 2. The constant multiple rule was Rule 3. So on and so forth. But anyway, once you've got this, you just simplify it. So you have f prime of x equals 24 x to the 7th minus 6. That's it. So make sure that you're simplifying once you take the derivative. I'm going to give you points for just taking the derivative, but if it's not simplified, you won't get full credit. You can't like leave your answer like this. You have to get me to the next simplified version of the expression. Example 2, this is g of x equals 7x to the 5th minus 3 over x plus 4 times the square root of x plus pi. So there's a lot more going on with this. The most important thing that I want to point out, well, there are 2 really big things here, but probably the most important thing would be this term here, the minus 3 divided by x. The x is in the denominator. I didn't actually give you a rule for derivatives where the x was in the denominator. You have to move that up to the numerator if you're going to use these derivative rules. So that's the big thing. The other thing is we're going to have to rewrite the square root of x using an exponent rule for radical functions. I'm going to rewrite these rules for you because it's probably been a while since you've had to use some of them. Some of you maybe had algebra really recently. So before we take a derivative, we need to make sure that our expression is set up so that we can fit it to the rules we have. So we're going to have to rewrite it before we take the derivative. So I don't remember exactly what the algebra rule was, but I'm going to put in my own little variation of this here. 1 over x to the a power is just x to the negative a. So that was an algebra rule. We used it on the first page when I was talking about switching that negative exponent to a positive. We're going to have to use a rule like that here. So in this case, a would be 1 because you have x to the first in the denominator. But that's an algebra rule. If you have a negative exponent in the denominator, you would move that up into the numerator as a positive exponent. So you won't be seeing that as often, but it's definitely a possibility. The big one, the really big one, is the nth root of x to the mth power. And by the way, this is the same thing as saying the nth root of x to the mth power. Those are the same. And this is x to the m over n. So when you rewrite your radical expression using a rational exponent, the value in the numerator is always whatever exponent was on x, and the value in the denominator is whatever the index of your radical was. So we're going to be using these rules quite a bit today to rewrite our expressions so that we can take their derivatives, but we have to rewrite the expression first. So I'm going to say first, rewrite g of x to fit derivative rules. Okay, so I'm not taking the derivative yet. I'm just getting the function set up so that I can take the derivative of each term. So I'm going to rewrite g of x, not g prime, because I'm not taking the derivative yet. The first term can stay as is. This is 7x to the 5th. We don't need to rewrite it. But the second term we do need to rewrite. I need to make sure that the x is out of the denominator. In order to move it out of the denominator, I'm going to pull it up and make the exponent negative. So 1 over x is the same as x to the negative first power. You can think about this as being x to the first in the denominator. And when you move the x up to the numerator, it switches the exponent's sign. Now the square root of x is x to the 1/2 power. So that one you're going to see quite a bit. The 4 is just going to stay in front of the function or of that expression. And then the pi is still just pi. Maybe since we just rewrote the pi, we should talk about the fact that pi is a constant. Because pi is represented by a symbol, students tend to always think of pi as a variable. But remember that pi is just a number. So pi is a constant. So when you take its derivative, you're going to use the constant rule. Okay, but now it's all set up so that we can use the derivative rules that we have to find g prime. All right, so we have g prime of x equals, we're going to keep that constant multiple out front. We're going to bring the 5 down, rewrite the x, and decrease the exponent by 1. I'm going to do the same thing in the second term. I'm going to leave that -3 out front. I'm going to bring the exponent down. I'm going to rewrite the x, and I'm going to decrease the exponent by 1. It's a -1. So when I decrease it by 1, it now becomes -2. All right, I'm going to rewrite this 4. I'm going to bring the exponent down. I'm going to rewrite the x. And when I decrease the exponent by 1, I'm taking 1/2 minus 1, which brings me to -1/2. And the derivative of a constant is 0. So the derivative of pi is 0. Now, once you find the derivative, that's most of the work, but we still need to simplify this. Now, I don't care if you leave negative exponents in your answer. You'll have to check what WebAssign wants you to do for your homework. But if it says to make all your exponents positive, do that. I'm not so worried about that. I mostly just want you to simplify anything else that's going on in the expression. So we'll have 35 x to the fourth plus 3x to the negative second plus 2 x to the negative 1/2. Another way that you could write this, if we were going to say no negative exponents, would be g prime of x equals 35 x to the fourth plus 3 divided by x squared plus 2 divided by, and then this is x to the negative half. So when I take x to the negative half and make it x to the positive half in the denominator, I can also just call it the square root of x in the denominator. So get comfortable working your way back and forth between these forms, because if we have something like this and we have to take its derivative, we'll have to rewrite it and so on and so forth. Let's see. I mean, we already kind of talked about this. You cannot take the derivatives. Oh, yeah. Make sure, I'm going to say note, if f of x equals 1 over x, we cannot say that f prime of x is like 0 divided by 1. You can't take the derivatives of the numerator and denominator separately. You have to be able to match a rule. That's one thing that makes this a little bit trickier. You can't just be willy-nilly just taking derivatives wherever the expression lies in a fraction. You can't do that. You have to be able to fit a rule. So I'm just going to say you cannot take the derivatives of the numerator and denominator separately. Later on, in the next section, I'm going to give you a rule for taking the derivative of a quotient. And for that rule, you're going to have a special formula that you're going to learn in order to take a derivative of something like this if you don't rewrite it. Not every quotient can be rewritten to use a rule from 3.1. But 1 over x can. So we rewrote 1 over x, or it was 3 over x when we had it, as x to the negative first. So you're going to have to rewrite it to fit a rule. You cannot take the derivative of the numerator and divide it by the derivative of the denominator. Students always want to do that. You cannot do that. I don't know how to emphasize this anymore. You cannot just take the numerator of the derivative of the numerator and divide it by the derivative of the denominator. I don't want to keep talking about that. It's important. We're going to talk about it again in the next example. So I am going to keep talking about it. I seem to have lost my page 1. Oh, here it is. Okay. Excellent. Okay, so let's do another one. I've got one more example here that I'm going to put for you on the top, and it's basically illustrating this same idea. So this will be example 3, and it's y equals, and I'm going to give you a fraction here. The numerator is 3x to the fourth minus 7x minus the cubed root of x squared divided by 2x. Okay. So remember, you can't just rewrite the numerator and take its derivative and then divide it by the derivative of 2x. You cannot. Don't even think about it. We're going to have to rewrite this, and I'm going to give you another algebra rule to do that in case you do not remember. Okay. The algebra rule we're going to use a lot here. You're learning now that you didn't take algebra just for nothing. It's so that you could apply all that to what you're going to be doing in calculus. If you have the same base and you are dividing, you subtract the exponents. So that's a rule we're going to use quite a bit. The counterpart to that rule would be if you are multiplying with the same base, you add the exponents. I don't know if we're going to use that for this particular problem, but that's a really important algebra rule that you're going to need throughout this whole simplify and find the derivative lesson. Okay. So I got to do a couple of things. If I'm going to use this algebra rule, I really need to have this expression, the cube root of x squared, written with a rational exponent. A rational exponent means a fractional exponent. So I'm going to go through, I'm going to rewrite this a little bit, and then we're going to use this rule. Now, if you're asking, like, wait a second, how can we use this rule? We don't always have the same base. That's true. We're going to have to go through and split this up. When you are dividing some sort of polynomial by a monomial is a one-term polynomial, you divide each term by that monomial. It's kind of like considering the fact that we could have only subtracted these if we had the common denominator. You're going to split that fraction up. So you can do this in any order. Maybe I'll split the fraction first. It is up to you. So I'm going to rewrite this as 3x to the fourth divided by 2x minus 7x divided by 2x minus. Now, when I rewrite this again, I'm going to rewrite this using that rule where I have the nth root of x to the mth power, and then x is going to become x to the 2/3. Remember that your index is always going to be the denominator. So thinking back to this rule that I gave you, if you have the nth root of x to the m, that n is going to go into the denominator, and the exponent is going to go in the numerator. So that's x to the 2/3 power. And this is going to get divided by 2x. Now we're going to simplify each one of these. Sometimes I have students who are like, I don't get it. How did you do that? Just think about it. If you are adding and subtracting, as long as you have the common denominator, you can just rewrite the whole expression over that denominator. We're just sort of undoing that by splitting up the fraction using the common denominator and then like undoing it. So back in algebra, you might have done a whole bunch of work to take this and turn it into that. But we're gonna rewrite it here. Still, I haven't taken a derivative yet. We're just rewriting so that we can take a derivative. So 3/2 is going to stay that constant multiple. And now what I'm going to do is I'm going to take this base, which is x, and I'm going to write it to the m minus n power. So I'm going to take the power from the numerator and subtract off the power in the denominator using that rule for algebra. We have the same base in the numerator and denominator. That base is x. We'll subtract off the exponents. Now, for the next term, you can see that those x's are just going to cancel. So you can just write that as 7/2, and then the x's are going to, x over x is 1. For the next term, I have a 2 in the denominator and technically a constant multiple of 1 in the numerator. So I'm going to write this as 1/2. And then I have that same base, which is x. And I'm going to write this as 2/3 minus 1. Again, using this algebra rule where if I have the same base and I'm dividing, I'm going to subtract the exponents. Still haven't taken a derivative yet. We're still just rewriting this expression so that we can fit it to these rules. So we have 3/2 x to the 3rd power minus 7/2, and that's just going to be your constant function, some function c. Now, this one, I'm going to leave it with a negative exponent because I need it to have a negative exponent if I'm going to use my power rule. So this is going to be minus 1/2, and then 2/3 minus 1 is 2/3 minus 3/3. You can always do this in your calculator, which is negative 1/3. By the way, most of you probably already know this, but if you don't, I don't want you getting these wrong because you can't add and subtract fractions. I mean, I'm kind of beyond that at this point. So one thing I was going to show you was, hold on, let me adjust for my lighting situation. Oh, there we go. Better. Okay. If you wanted to find 2/3 minus 1, you'd enter 2/3 minus 1. Your calculator, of course, will give this to you as a decimal. If you want to turn this into a fraction, you hit the math button and then you hit enter twice. And it'll give you negative 1/3. Sorry, the lighting is still not great, but ooh, it could be so much worse. All right, so it actually seemed to have gotten worse since I entered it. I used to do this in my night class because the light was all funny. Okay, so you can enter math, enter, and you'll get the actual fraction form of that. So negative 1/3. Now it's set up to use our derivative rules that we've talked about in this section. So we haven't taken a derivative yet. Now we're going to. I'm going to just call it y prime. You call it whatever you want, but since I gave it to you as y, we'll call it y prime. Notice how we did not take the derivative of the numerator and divide it by the derivative of the denominator. That will not work. You will not get the same thing. This would require the quotient rule, which we're going to learn later on. But let's go ahead and use our derivative rules now. So we'll have 3/2 times, we're going to bring the exponent down and decrease the exponent by 1, minus, you don't have to write the 0, but the derivative of 7/2 is 0. And now you'll have minus 1/2 x to the negative 1/3 minus 1. I'm just writing that one out because you're going to have to subtract 1 from negative 1/3. Well, luckily I have negative 1/3 in here already. If you can see it, if I say minus 1, it gets me to negative 4/3, but it's negative 1/3 minus 3/3, which is negative 4/3. All right, so you're going to simplify this here. You can multiply the 3's together to get 9. So you'll have 9/2 x squared. And then for this term, you're going to have minus 1/2. And then x to the, oh, you guys, I forgot to bring this negative 1/3 down. I was so focused on having you rewrite this exponent. Sorry, I totally forgot to bring the exponent down. It belongs in here. I'm going to make a little space for it. Some of you were sitting at home like, wait a second, why didn't she? Sorry. I sometimes get so focused on doing one thing that I forget to do something else. Okay, so this is the 1/2. When I bring the exponent down, I'm multiplying it by negative 1/3. See if we can fit it in there. So really, we're going to have here plus 1/6. So it's minus a negative, which turns this into a plus. And then the 2 times 3 gives us 6. And then we'll have x to the negative 4/3. I'm okay with this answer. You could also rewrite this with a positive exponent as 9/2 x squared plus 1 over the 6 stays in the denominator. X moves down into the denominator with a positive exponent of 4/3. Either one of these, though, is completely fine with me. Okay. Let's bring this back to what we were talking about in 2.6, which was finding equations for tangent lines to the curve. That's not going anywhere. So we're going to practice that a little bit more here. I'm going to give you a function, f of x equals x plus 2 times x minus 1. Now, this function is specifically being given to you to throw you off a little bit. The idea is we cannot just take the derivative of x plus 2 and the derivative of x minus 1 and multiply them together. Do not, I'm going to say, don't do this. F prime of x equals 1 times 1. So this is a big no. Do I have a big red pen somewhere around here? Where's my big red pen when I need it? This is a no. I know it's a double negative. Don't do this. No. You cannot just take the derivative of each factor and multiply those together. This would require something called the product rule, which you're going to learn about later in the chapter. For today, I'm going to show you how to simplify this and then take the derivative. So we're finding the equation of the tangent line to the curve. In order to do that, we need to find a slope. A slope is a derivative. So we're going to rewrite our function f of x, and we're going to rewrite it by foiling this out. So you're going to get first terms give you x squared. The outsides give you minus 1x plus 2x, which is just going to be plus 1x. And then the last terms give you minus 2. So this is your function rewritten so that it's no longer a product of functions. Now we can use our derivative rules on this. So we'll take f prime of x equals, I'm going to bring the exponent down, decrease the exponent by 1. The derivative of x is 1. That was that rule that I added. And the derivative of a constant is 0. So hopefully we're getting kind of more familiar with this and we don't need to write all the extra information. We're supposed to be finding the equation to the tangent line at the point 2, 4. So that means I'm looking for the slope at 2, 4. 2 is the x coordinate. So I'm looking for the slope when x equals 2. So I'm going to take f prime of 2. This is very similar to what we did in 2.6, except our derivatives are coming much more quickly. I'm not taking f of a plus h minus f of a, or f of x plus h minus f of x divided by h. Not doing that right now. This is much easier, right? 2 times 2 plus 1 equals 5. So this is the slope when x equals 2. And if I'm finding the equation to the tangent line at this point, well, you have a point, you have a slope. Remember that when you are looking for the equation, when you have a point and a slope, it's, I think, best to use point slope form. So I'm going to take my point. The y coordinate was 4. The slope we just found was 5. And the x coordinate was 2. And I'm going to rewrite this to solve for y so that it's in slope-intercept form. So I'll have y equals 5x minus 10 plus 4. So y equals 5x minus 6. That is the equation of the tangent line at 2, 4 to the curve. Remember that you can always check this by putting this curve into your calculator and then putting your derivative function into your calculator. Or actually, you don't even really have to do that. All you really need to do is put this curve into your calculator and then put this equation for the tangent line into your calculator. And you should find that this hits your graph at exactly this 0.24 and it's tangent to the curve there. So next we're going to find the equations of the tangent lines when the slope is 4 for the curve. So this time you're being told that the slope is 4. So what we're going to do is we're going to take our derivative, which we found previously already, f prime of x is 2x plus 1. And we're going to take that derivative and set it equal to 4. Because you're being told the slope is 4. The slope is a derivative. The slope is a derivative. That's what that means. Slope is 4. F prime of x equals 4. And we'll solve for x and figure out where that actually occurs. And this one we're probably going to look at in our calculators. I think it'd be really helpful. Subtract 1 from both sides and divide by 2. And you get x is 3/2. Now, this is the x value where the slope is 4. Remember that I'm looking for a point on this curve. The curve is up here. So what I need to do is now to find the y value, find y when x equals 3/2. So in order to do that, I'm just going to find f of 3/2. If you prefer to write this as 1.5, that's okay. I will leave that up to you. If you prefer to put that into the original form instead of the one you rewrote, that's also fine. It's up to you. So I'm going to just keep this in the rewritten form. 3/2 squared plus 3/2 minus 2. I'm just trying to find a point on the original curve. Once I have the point on the original curve, I can verify that the tangent line that we find is actually tangent to the graph at that point. So f of 3/2 is the y value. When x is 3/2, you end up with 9/4 plus 3/2 minus 2. And feel free to put this into your calculator. If you can see mine, this is 9/4 plus 3/2 minus 2. And you get 1.75, which if you hit the math button, enter, you will see is 7/4. Okay, so your point is 3/2, 7/4. And your slope was given to you as 4. In order to write an equation for the tangent line, you need a point and a slope. So we're going to put this together now to find that equation. So y minus y sub 1 is m times x minus x sub 1. So we have y minus 7/4 equals the slope, which was given to you as 4, times x minus the x coordinate at that value, which is 3/2. So we'll distribute 4 times 3/2. Well, 4 times 3 is 12. Divide that by 2 and you get 6. And then we'll go through and add 7/4 to both sides. And again, you can do that in your calculator. I'm just going to say -6 plus 7/4 is -4.25. Math, enter, is -17/4. So my equation is y equals 4x minus 17/4. If the slope is 4, you're looking for the rise over run to be 4. So we can go ahead and put this function into our graphing calculators. I'm going to enter it the way that it was originally presented to us, which was x plus 2 times x minus 1. And then zoom 6 to zoom standard. First of all, if you wanted to see the equation for the tangent line at the point 2,4, we had that as 5x minus 6. Whoops. Uh-oh. I'm going to have to rewrite this. Okay. We'll do that. 5x minus 6. And then you can see that that tangent line is going to be tangent to the graph at the point 2,4. So here's your graph again. Here comes the tangent line. You can eyeball it, but you can also zoom in if you'd like, but you can see that it does appear to be tangent at 2,4, so that's good. But I'm going to go ahead and instead of the 5x minus 6, I'm going to go with this number 2 that we did, 4x minus 17/4. Now you know that this line has a slope of 4 because it's y equals mx plus b, and 4 represents the slope. So now we can graph the curve again with your new tangent line. And you can see that this is tangent to the point 1.5 and then 1.75. And the slope is indeed 4 because that's what matches our equation. So 1.5, 1.75, that's what you're seeing here on the graph. And that's where you have the slope being 4. If the slope was greater, for instance, when we moved that point to the right, when we had it at 2,4, if we were to move that point to the left, you would see that slope start to shallow out as we headed towards the vertex at some point would be a slope of 0. Okay. All right, so that is an application that was similar to what we did in the last section. Now we'll do 2 application problems where we're going to be talking about this special wording that we're going to use anytime we need to use the derivative. The percentage of families that were married couples with children between 1970 and 2010 is approximately P of T equals 49.6 divided by T to the 0.27. We're going to rewrite that in a second, where T is measured in decades with T equals 1 corresponding to 1970. What percentages of families were married couples with children in 1990, and how fast was the percentage of families that were married with couples changing in 1990? Okay, couple things here that we need to decode. First, we're going to be using this function p of t, and we're talking about derivatives, so you have a really good sense that we're going to have to take the derivative of this function, and you would be very smart to think so. I'm going to rewrite this as 49.6 times, I'm going to move the t up into the numerator, and I'm going to have to make the exponent negative when I do so. All right, so now we have 49.6 times t to the negative 0.27. Okay, that's first things first. You're being asked two questions here. Question one, what percentage of families were married couples with children in 1990? Well, we're going to find that just by using the original function. This function gives us percentage of families that were married couples with children. That's what this equation is going to give, percentage of married couples with children. Where the derivative comes in is when we talk about how fast was the percentage changing. When we talk about how fast was that percentage changing, we're talking about a rate of change. Which means we need the derivative. So you're going to see a lot of application problems in this chapter, and you're going to usually be asked a couple of things. Some of them are going to relate to the original function, and it's just going to say, like, find the percent. And then you're going to be asked something different, like find the rate at which the percent is changing or something like that. When you're talking about the change in the value, that's where you're looking at the derivative. So these are the key words that you're going to be looking for as you go through these application problems. It might not stand out to you right away, but as you start to work through them in each section, you'll start to notice, like, oh, okay, I'm using the original function because I'm just being asked for this value. Now they're asking me for how fast is this changing, which implies derivative. Okay, those are a couple important things. The other one is, if we're going to be talking about 1990, we need to figure out the value of t. T is measured in decades, with t equals 1 corresponding to 1970. Decades, not years. So it's very normal for us to want to say that t is somewhere in the 20s, because you're like, oh, well, 1990 is 20 years after 1970. So 1 plus 20 is 21. T is not 21 because t is measured in decades. That matters. So if t equals 1 corresponds to 1970 and t is in decades, well, that means t equals 2 corresponds to 1980 and t equals 3 corresponds to 1990. This is a very common way that your book and WebAssign is going to be wording these problems. It's really important that we can interpret that information to come up with the quantity that we need for our variable. All right, so now that we figured out what t represents in 1990, we can start to answer that first question. What percentage of families were married with children in 1990? All right, so that means that I'm looking for the percentage when t equals 3. And for that, I'm just going to be evaluating this function at 3. I'm going to put this into my calculator because I'm going to get a decimal. So I have 49.6 times 3 to the negative 0.27. And we end up getting 36.8687. Okay. And remember that this is giving you a percentage. I know sometimes when we're asked for percentages, we multiply our numbers, our values by 100 to get it to be a percent. But this is already giving you that p represents a percentage. So when we get this, this is already a percent. 36 point, let's call it 87%. So this is the percent of couples who are married with children in 1990. So 36.87% were married with kids in 1990. Married with children. Okay, so that's one answer that we're looking for. The other one is, how fast was the percentage of families that were married couples with children changing in 1990? Okay, so let's find that. If we're looking for a rate of change, we need the derivative. So first, we'll find p prime of t. I'm going to leave my constant multiple in front. I'm going to bring down the exponent. I'm going to rewrite my t, and I'm going to decrease the exponent by 1. So if I'm at negative 0.27 and I take one more away, well, now I'm at negative 1.27. All right, so now I have my derivative, and we're going to evaluate that at t equals 3 to determine how that percentage was changing in 1990. So I'm going to take p prime of 3. Excuse me 1 second. Hold on. All right, the 4-year-old is still homesick, and every time we leave the room, we must leave the TV blaring as loudly as possible with the door open. Okay, so let's go ahead and evaluate. So we have 49.6 times negative 0.27 times 3 to the negative 1.27. So I'm going to enter this into my calculator, and let's see what we get. So we have 49.6 times negative 0.27 times 3 to the negative 1.27. One thing I want to mention right away, and I probably should have mentioned this before also, because this is a very popular thing that students like to do. Do not multiply the base of this exponential expression by 49.6 and then take that to the exponent. Remember, the order of operations says you do an exponent before you multiply. So your calculator knows, if you enter this correctly, to take 3 to the negative 0.27 and then to multiply it by 49.6. It knows to do that here also. So don't multiply 49.6 times negative 0.27 times 3 and take that quantity to an exponent. That's not what you're doing here. You can multiply 49.6 times negative 0.27, but that quantity is getting multiplied by 3 to the negative 1.27. So it's not the same thing. If you enter it into your calculator like this, it knows to do the exponential expression first. Okay, so you get negative 3.32-ish. Negative 3.32%. So it's really important here to note that your answer was negative. If we're talking about how a quantity is changing over time and the percent is negative, that means that the percentage is actually decreasing over time. So that we could say here that the percentage in 1990, the percentage in 1990 was decreasing at a rate of about 3.32%. Um, 3.32%. And when we talk about that percentage, we are thinking about that as changing per decade. Because it's changing over time, and the quantity that you are looking at regarding time is in decades. So in 1990, the rate was decreasing at about 3.32% per decade. Sometimes I think we need to mull over this derivative stuff in our head a little bit to make it make sense to us. But if you know anything intuitively about population change, recently they keep saying like, oh, the population is not growing fast enough. I think it makes a little bit of sense that number was decreasing, or maybe fewer people are getting married and having children. More people are just deciding to partner in life and have children. But there are lots of changes occurring. People are deciding not to have children. So I think logically this answer should make sense to us, and that each decade it's changing by about 3.32% in the negative direction. Last but not least, we must talk about a little bit of projectile motion here. The function s equals f of t equals negative 2t cubed plus 114t squared plus 480c plus 1 gives the altitude or the height of a rocket in feet at t seconds. Find the maximum height or altitude of the rocket. Okay. So if you were to graph this function, by the way, let's graph it just to see what happens. This is going to give the height of the rocket at a given point in time. So the function is negative 2t cubed plus 114t squared. We're using x here, of course, because that's what our calculator likes, plus 480t plus 1. We're going to have to do a little bit of work with the zoom here. I'm going to start out at zoom 6, but we'll have to get a sense here for how, yeah, that happens. Okay, and it's already done. So a lot of this important information we're missing. So the y coordinate here, oh goodness, I mean, I'm sort of at an advantage here because I know what the maximum height is supposed to be. Let's see. Well, we know we can't have negative time. Let's see, a rocket is going upwards. Let's see, let's change our y max to 10,000. Technically, we don't really need the y min, but we'll keep it right there for now. All right, it's going up. We're gonna have to increase what's happening on the x-axis. So let's make the x max 100 maybe. See what happens. All right, that function is continuing to go up and then it comes back down again. We are clearly not high enough on the y-axis. But again, notice how I'm just playing around with these numbers. I wonder what happens if I add an extra 0. Can my calculator handle this? Oh, it can. Good job, calculator. All right, so this is a cubic function. If you were to graph some more pieces of it over here, you'd find another leg. So if I know I made my x min 0, but let's say I made it negative 100, you'd see more of what's actually happening with this graph. Okay, so it's cubic. We know that it's got this sort of shape that's based off of what you did in algebra. We are not concerned, though, with what's happening to the left of the y-axis, because remember, the y-axis is representing time. So I'm going to send this back to 0. I just wanted you to get a fuller picture of what was going on with this graph. Okay, so this function gives the altitude of a rocket in feet. So that means the y-axis represents feet, and then we're talking about that over t seconds. We're going to find the maximum altitude of the rocket. Well, if you play around a little bit with this, you saw that I had my y max set all the way up to 100,000. So we're looking for this value. Find the maximum, yes, find the maximum height of the rocket. So we're trying to figure out what this y value is. In order to do that, we're going to use derivatives. The nice thing is, I've kind of talked about this a little bit. If we were only looking at what happens on the way up to the maximum, and you were trying to take the slopes of the tangent lines, your slopes of your tangent lines are not vertical, but they become steeper as you move up your way through here. But as you get to the top where you have this maximum altitude, suddenly your tangent lines become horizontal here at the top. And then as you move your way back down the hill, your tangent lines start to go negative because your graph is heading downward. What we're looking for is this exact point in time where the slope of the tangent line is 0. Now, remember that happens at 2 different places, because when we had our x minimum here, I know I could have made it smaller, but that's okay. You are actually going to find 2 different values for this. One of them is going to be right here, where you have a slope of the tangent line being 0. The slope of the tangent line will be 0 anytime you have some sort of a valley or a peak. You're hitting either a minimum or a maximum. This is something we're really going to be exploring in chapter 4. So we're kind of like building that foundation here in chapter 3. I need to find out where f prime of t is 0. Find where f prime of t equals 0. And then this is going to give us the x coordinate where that occurs. And then we're going to solve to find the y coordinate at that value, or the, I guess, s coordinate at that value. All right, so the maximum altitude occurs when the velocity equals 0, and the velocity is the derivative. So that's another way of thinking about that. This occurs where the velocity is 0. That means that f prime of t equals 0. Remember, the velocity is the derivative of the position. And if we have the velocity being 0, you have the rocket going up, 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 and all of a sudden the velocity is 0. Then it goes back down again. So you think about how this however you want. I guess I was thinking about it more in terms of tangent lines and slopes, since we've been talking about that a little bit more. But if it helps you to think about finding where the velocity is 0, then do that. So let's take f prime. So I'm taking my function here. I'm going to just use my rules, bring that 3 down, and then I have this written as 2 cubed plus 114 times 2t plus 480. So the derivative of 480t is just 480. And then I'm going to evaluate this. I guess I could simplify it first. It really doesn't matter because we're going to be evaluating it. But this gives us negative 6t squared plus 228t plus 480. Well, yeah, of course we needed to do that. What was I thinking? Okay, we're taking the derivative and setting it equal to 0. Let's hope that 6 is a constant multiple here and we can take out this GCF, because if I'm going to figure out where I have these two places where the slope is equal to 0, then I need to solve this quadratic equation. So I'm going to take 228 and divide it by 6, and I do get 38, and 480, of course, is divisible by 6 because 48 is divisible by 6. So let's solve this equation. I'm going to take out the GCF of negative 6, and that leaves me with t squared minus 38t minus 80 equals 0. And then we'll factor this. If you can factor it, just factor it. It makes your life so much easier. I'm looking for two numbers that multiply to give me negative 80 and add to give me negative 38. So that will be negative 40 and positive 2 equals 0. All right, now negative 6 equals 0. That means nothing to us. We can omit that. So we have t equals 40 and t equals negative 2. Oh gosh, I was looking at my graph and I thought it occurred at t equals 0, but apparently it is occurring at t equals negative 2. Remember that t, though, represents time. You can't have negative time. So we're going to have to use this value, which means that t equals 40 seconds. But don't put a box around it and be like, okay, I'm done. We're good. You were not asked to find the value of t when it hits its max. You were asked to find the actual maximum altitude of the rocket. So that means that you need to find the height of the rocket at t equals 40 seconds. So for that, you're not looking at the derivative anymore. You're not talking about the slope or the velocity. We're not talking about the velocity at 40 seconds. We're talking about, I mean, we already know the velocity at 40 seconds is 0. That's what you just solved for. We're talking about the height of the rocket at 40 seconds, and the height of the rocket's given by your function f of t. So we're going to find f of 40. So f of 40 is negative 2 times 40 cubed plus 114 times 40 squared plus 480 times 40 plus 1. And when you put all of this into your calculator, I was going to let you do that, but I guess I'll put this into my calculator. Negative 2 times 40 cubed plus 114 times 40 squared Again, if you enter this correctly, your calculator will do the order of operations properly. Don't multiply 114 times 40 and then square it. That's not the same thing. Plus 480 times 40 plus 1. And you get 73,601. And again, don't just put a box around it. You need to know 73,601 what? This is an application problem. You can't just leave it. So the altitude is given to you in feet at t seconds. So this answer would be feet. If I was using the derivative, I would be talking about feet per second. And that means we set the derivative equal to 0. The velocity was 0 feet per second. Okay, so those are just some application problems that you're going to be using with the derivative. We're going to be showing applications in every single section every time you learn new derivative rules. The next section, we're going to actually talk about what to do when our functions are products and quotients. And maybe we can't simplify them using algebra rules. We're going to talk about rules for how to take derivatives of products and quotients. And then after that, we'll talk about my favorite rule, the chain rule. So there's so much to look forward to in business calculus with this chapter. It's an awesome, awesome chapter, and I'm very excited. So get working on that homework. Get yourself off to a good start with chapter 3. It's not too crazy of a chapter. It's probably going to be, I want to say it'll be the easiest chapter you're doing in this class, but everyone's got their strengths and weaknesses. Have a wonderful rest of your day and enjoy working on your derivatives.